Welcome you to Cambridge, to the Centre for Mathematical Sciences, which is where we're located, in particular Centre for Mathematical Sciences over there, to the Institute, and to this first workshop in the Stochastic Partial Differential Equations programme. And I want to say something about the Isaac Newton staff, because I've been working as Deputy Director of the Isaac Newton Institute for a year now. And I've always been impressed about the dedication and professionalism of the staff. The staff at the Institute, they are knowledgeable, they're friendly, and they are here to help you. That's their mission in life, so to speak. And so if you have any questions or queries, please don't hesitate to ask a member of the Institute staff. Now, this workshop is being organised by Heather and Chia primarily, but also we've got Steve, who is going to be in the room at the back, and he's not going to operate all of these cameras that you see around the room in order to provide a resource for the world mathematical community. We're currently adding 500 videos to our video collection annually, and it's becoming a major resource. So I would like to ask you to thank all the Isaac Newton staff, but in particular Heather and Chia and Steve, if that's okay. And finally, I just want to make sure that you're fully aware of the most important event of the day, which of course is the wine reception at 5:30, which will take place in the lobby here. So please do come along, and I hope it's going to be a great meeting. Thank you.
Yeah, thank you very much for the nice introduction. And of course, in the name of all the organizers, we're of course very happy to be here. And I heard some rumors that today is even Newton's birthday. Jonathan told me, but I haven't confirmed yet. That would be, of course, a fantastic coincidence.
Christmas Day.
Sorry?
Christmas Day.
It was Christmas Day, so it's not too long ago.
It's two different calendars, old style or new style, Gregorian or non-Gregorian.
Okay, so we really
Today
have to
is
sort
new
it out.
style, not Gregorian.
Let's glow.
Okay, so this is the first problem of this meeting, to find out which is the right birthday of Newton. Okay, so it's a pleasure for me to announce the first speaker today. So it's Giuseppe Da Prato, and he's going to talk about elliptic equation in open subsets of infinite dimensional Hilbert spaces.
Thank you. First, I want to thank the organizers of the invitation. I am very glad to be here at the Newton Center for this very interesting semester. I will talk about elliptic equation in infinite dimensional space. So I will consider an equation of the form 1. L is an elliptic operator.
Your microphone.
What else to do?
Can you put it there?
It's here.
I think it's probably gone off.
Okay, it's better. So L is a second order elliptic operator. I will be more precise in a moment. Lambda is a positive number, f is a given function, and the equation is set in an open subset of the Hilbert space H. And obviously one has to set some boundary condition on the boundary of O, and I will consider Dirichlet or Neumann condition. So let me give the explicit form of the operator. So the operator is an Orff-Uhlenbeck operator. It is possible to develop the theory also for more general operator, but I will just consider this operator. So in fact, it's a family of Orff-Uhlenbeck operator depending on a parameter alpha. You take alpha in 0, 1, you take a trace class operator Q, then one can consider Q has the covariance of a Gaussian measure mu of mean 0. And all this family of operators has the common property that they has the same invariant measure mu. If one do a very simple explicit computation, you see that for any alpha, the invariant measure of the operator L alpha is equal to mu. That is the Gaussian measure of mean 0 and covariance Q. For instance, when alpha is equal to 0, this is the Orte-Nuremberg operator of the Mayaven calculus. And when alpha is equal to 1, this is in a sense the best Stromfeller Orte-Nuremberg operator. So the operators are very different when alpha varies, because they enjoy very different kind of properties. But the invariant measure mu is the same for all this family of operators. So the plan of the talk is the following. In the first part, I will give some notations, and I will discuss some integration by part formulae. Integration by part formulae are a very essential tool when one is studying boundary problem, because one has to perform some integration by part on the boundary. And so this is a basic tool that I will need. In the second part of the talk, I will speak about the Neumann problem, and the last part, the Dirichlet problem. And the talk is based on some joint papers, and concerning the points 1 and 2, Neumann problem, is a paper in collaboration with Barbu and Tubaro. And for the paper 3, it is a paper in progress with Lunardi. Before giving notation, let me give a bit of story. And the study of elliptic equation and potential theory in infinite dimension was essentially started by Zaleski and Gross in the 60s. There were some results due to Levy before the war, but in fact the Levy potential, the Levy Laplacian, and so on. But the important part of the theory we started with Zaleski and Gross. And there are several further developments. For the moment, I will just quote some books. The book by Zaleski and Fomin, the book by Cerrai, and the book by Zabchik and myself. Other reference I will give later. The most part of the problems that were studied concern elliptic and also parabolic equations in the whole space H. There are not many results concerning elliptic problems in open subsets. Concerning the Dirichlet problem, I will quote two papers, a paper by Goldis, Zabchik, and myself on Conferendu, and also a long paper by Talarczyk in Studia Mathematica. Also, about this paper, I will precise in a moment the meaning. This for Dirichlet. What about Neumann? For the Neumann problem, the only result I know before the result I will speak today is a paper by Zambotti in PTRF 01, who studied the Dirichlet form related to the Neumann problem when the space H is L201 and the open set is the closure of the set of non-negative function. I have to notice that this set is very singular, and in the remaining of the talk, so K is not the closure of an open set. This is clear because has empty anterior. So this is a very complicated case. In my talk, in the sequel, I will consider problems in bounded, in open sets. So I will not recover this result by Zambotti. This result by Zambotti is related to reflection problems, scorer problems in infinite dimensions, in the basic paper studied in the basic paper by Noirard and Pardue in '92. And an application, a similar model with an application to interface model was gave rise to a paper by Funaki and Olla in '01. So now I start with notations, and then with integration by part formulae. In this notation, I will repeat what I said before. In a sense, mu is a non-degenerate Gaussian measure in the Hilbert space H with mean 0, a covariance Q. And I will consider a complete orthonormal system which diagonalizes Q, Q ek equal lambda k k. And then I will consider the Orsten-Uhlenbeck before, or better, the family of Orsten-Uhlenbeck operators I have written before, which is again. I repeat also that mu is the unique invariant measure, is a unique infinitesimal invariant, but also invariant measure, because one can show that this operator L alpha in fact generates a strongly continuous semigroup, which is the Orsten-Uhlenbeck semigroup, and the mu is the unique invariant measure. One can check very easily that the operator L alpha is symmetric, and also this integration by parts formula holds. In the right-hand side, one has the corresponding Dirichlet forms. You see that the fact that I am considering this family of operator L alpha has as a consequence that the Dirichlet form will depend on alpha. Again, when alpha, the limit case, when alpha is equal to 0, this is the Dirichlet form of the Maillard calculus, and when alpha is equal to 1, this is the Dirichlet form of the, in a sense, best Stromfeller semigroup. It is also well known that L alpha is the diffusion operator corresponding to a stochastic differential equations, which is written here. So if I call A the inverse of Q, since Q is a strictly positive, because I am considering a Gaussian measure mu which is non-degenerate. So the operator Q is strictly positive. That is, its eigenvalues as all strictly positive. As a consequence, the inverse of Q minus 1 is a self-adjoint operator which is strictly positive, and this is the stochastic differential equation which corresponds to L alpha, in the sense that L alpha is the Kolmogorov operator corresponding to this equation. There is a formula of the integration by part formula for Gaussian measure, which is really basic, which is the basis of all Maillard calculus, and which is well known. It is the formula which is written there. If I consider integral over h of the derivative in the direction ek, dh means the derivative in the direction of ek. The mu, this is just 1 of lambda h, integral over h, xh phi d mu. This is a well-known integration by part formula. This formula, using this formula, one can define the Sobolev space, because one can show that the gradient is closable and define the usual Sobolev space. Let me recall the basic space. The space will be W12 with this subindex Q1 minus alpha, and W22 with the same subindex Q1 minus alpha. And the semi-norms are just for the W12 is the integral over h of Q1 minus alpha over 2 d phi squared d mu. And then one has also a similar definition for the space W22 Q1 minus alpha. Again, let me notice the special case alpha equal to 0, alpha equal to 1. If alpha is equal to 0, then the Sobolev spaces coincide with the one of the Maillevin calculus, what in general are called D12, D22. And when alpha is equal to 1, they are just the Sobolev space, because then Q1 minus alpha is the identity, it is just the usual Sobolev space. So the first result is to define how to define a Sobolev space in subset K. So K is a set, a convex set. For simplicity, I take a convex set with non-empty interior for K. And the first result is to generalize the previous integration by part formula. And you see in that formula 1 is the formula I have written before, plus an additional term, which is the second term, which is a surface term. The surface term has this form, the EH component of the normal phi d sigma. So it is very simple. The problem is that one has to define which is the meaning of the integral of the surface. This I will explain in a moment. So this is a generalization of the previous formula. You see, the first hand side, the h phi d mu is the same as before, as the term in the right hand side, 1 over lambda h integral over k xh phi d mu. And there is this extra term, which is a term on the boundary. And on the boundary, one just have the h component of the normal, which is well defined, because the set K is a convex set with a regular boundary. And so, using formula 1, one can show closability of the gradient and so one can define closability, and one can define a Sobolev space in the K. So the idea is exactly the same as the problem is that one needs some result about the surface integral, and I will recall in the next slide. Starting from a continuous function f, then if f is any Borel function, one do the definition as usual by simple generalization. Let me start by a continuous function f, a mapping from H into R. So a natural idea to define the integral of sigma fy sigma dy is to consider this limit. The limit is the integral on a shell. It is a shell around sigma which tight H from one side to the other side. This is the side. For instance, if K is the ball, if K is the ball, you take this shell, this is H, and you compute the integral on the shell. It is important to notice that this limit exists, The first result I know in this direction is in the case of a ball K, B01. In this case, there is a very interesting paper by Hertel, which is of 80, who proved explicitly this limit. In the case of the ball, one can compute explicitly the form of the surface integral. And then there is a much more general theory developed by Maillevin. One can look also to the book by Bogachev for references. And the theory of Maillevin holds for very general sets. I will not be very precise, but they are defined. He considers sets K defined as the sub-level sets of a very regular function G. G is a very regular function. Very regular means for Maillevin it is infinity, and such that the inverse is integrable for all power p. For instance, this is trivially true in the case of the ball, but also in several other cases. For instance, one can consider set of this form. You take a linear bounded operator in H. Okay, you can consider the set of function t such that tx less or equal to 1. And in this case, this integration by part formula also. Now, using this integration by part formula, it's possible to prove, we use this formula plus a coarea formula, which is also due to Scorokod and Maillevin, and we proved the formula 1. Formula 1, I repeat, is an integration by part formula, which generalizes the classical 1, and we allow to define the Sobolev space in K. Once the Sobolev space are defined, one can try to define the trace. In general, the definition of a trace is a simple consequence of Green formula in the finite dimensional case. In this case, the Green formula is replaced by the integration by part formula I have written before, and using this is not difficult. This is easy. The previous result was not very easy because also relies on these general results on surface theory, but this is an easy consequence of integration by part formula. You see this inequality. In the second hand side, you have q1/2 the phi square. So, if this means that if you have a function phi, which is w12 q1 minus alpha k mu, obviously, for this function, the integral in the right-hand side is finite, because 1 minus alpha over 2 is less than or equal to 1/2. So for any function which is in any of this Sobolev space, it is well defined the integral of the square of the function phi on the boundary. But there is an extra term. There is this term q1/2 ny square. This means that we cannot say that the trace of phi belongs to L2 sigma, but just when it is multiplied by this extra factor q1/2 ny. So one can define the trace, but this is a technical difficulties in proving several regularity results. Okay. Oh, the same can be done for the trace of the derivative. In order to define the trace of the derivative, one has to consider a function which is w to 2. And then iterating this procedure, we can define the existence of the trace for the normal, for the second derivative, for the derivative. So this can be proved exactly in the same way. You see, in this case, in the right-hand side, we have something which is finite when phi is w to 2. This is just the norm w to 2. And the in the right-hand side. In the left-hand side, you have the trace of the derivative, but multiplied by qy minus alpha over 2. This means, for instance, that when alpha equal to 0, here you have the Maillard derivative. And also there is this extra term q1 alpha and y square. Okay. So one has integration by power formula in the space K, and also one has a good notion of trace for the function in this boundary, and also for the derivative. And now let me go to the second part of the talk, to the Neumann problem. And here there is some results which are very easy, because we have proved that the Dirichlet form I have defined before is closable, because the fact that one can properly define the Sobole space is equivalent to say that the Dirichlet form is closable, and then one can use the usual theory for weak solution, the Lax-Milgram theory. So this is just standard. What is not standard, which is more complicated, is to study the regularity of the solution of the weak solution. In particular, it is not standard to show that the weak solution attains the Neumann condition. So let me be more precise. So this is the usual definition of weak solution. Let lambda greater than 0 and f in L2 k mu. By weak solution of the Neumann problem, I mean a function phi which is w12 qy minus alpha, such that this is the usual condition, and A is the usual Dirichlet form. So this is the solution. Since we know that this Dirichlet form is closable, you can use Lax-Milgram theorem and conclude that there is a unique weak solution. Okay, this is quite standard. Just recall that I am considering very regular convex set. A similar result were obtained by Zambotti in the case when K is not regular. In the case of Zambotti, the integration by pair formula is similar to this one, but much more complicated to obtain. So in this case, this was just a parenthesis. So in this case, I can use the Lax-Milgram theorem and conclude that there is a unique weak solution. This is the so-called weak or variational solution. This is also the classical theory. One can define a self-adjoint operator in L2 k mu, which corresponds to the variational solution. This also is classical. In general, one defines the operator and alpha. First one defines the domain, is the set of function phi in W12, such that the Dirichlet form A phi v is continuous in L2 k mu, and the mapping v in A phi v is continuous in L2 k mu. This also is standard. One can define this operator. So there exists a unique self-adjoint operator n alpha such that integral of n alpha phi psi is equal to -1 half the Dirichlet form. In this case, you say that phi is a strong solution of the problem. Okay. This is completely classical. Now, the difficult problem, having finite dimension, it is not easy problem, is to study the regularity of phi. So no problem for weak resistance, for resistance of a weak solution. Now let's go to the regularity. For the regularity, one can prove the following result. Assume that lambda is positive and f is in L2 k mu. Then there is a unique strong solution of the Riemann problem, this we know, but here are listed some regularity properties. The function phi belongs to W22. Also, the integral of k a alpha over 2 d phi squared d mu is finite. And finally, phi fulfills the Neumann condition. This is indeed a conormal condition. This is natural, having infinite dimensions. This is a conormal condition which is given. Notice that the property II is not included in the property I. For instance, if you consider the case of, let us consider the particular case and when alpha equals to 0, then I means that phi belongs to the Maillard space dg2 h mu. And II means that the integral over h d phi square d mu is finite. You see that this condition is not included in this one, because to be in the space d22 h mu implies in particular that it is in d11 h mu. So this implies in particular that this is finite. So this is stronger. The second condition is stronger. And the third condition is Neumann. Now, let me do some remarks about maximal regularity results. At first glance, this seems to be a maximal regularity result. It is maximal in the sense that one can show, even in the case of Horst and Hurlebach in all the space, that one cannot improve this result. But it's not maximal in a sense as it is in finite dimension. Let me do a comparison with what happens in finite dimension. So in finite dimension, so H is a finite dimensional space, and then I take for Q identity, for instance. I could take also not identity operator, but let me take a Q identity, and then from the theorem 1, it follows that the domain of N is the set of functions which are in W to 2 with the normal derivative equal to 0 in sigma. And this is a maximal regularity result. This is the classical result that one can get in finite dimension. Here, what we can conclude? If H is infinite dimensional, we can conclude that phi possesses all second derivatives. which are in L2K mu. So the result is maximal in this sense. However, Q1 minus alpha d square phi is not of trace class, but it is of trace class only the square, which is weaker, because it means that the operator is Hilbert-Schmidt instead of nuclear. And so we cannot write that this equation holds. So this is morally the solution of this equation, but you can say only that the sum of the second and third term are meaningful, but not each term singularly. And this is a condition. This is not a lack of regularity of the theory. This is natural, because if you consider the Orsten-Uhlenbeck operator, that is, we consider the problem in all the space. In this case, you can do explicit computation using Hermite polynomial, because everything is diagonal. And you see, in fact, that this is the situation. Only the trace of the square is meaningful and not the trace of the operator. So this is a typical difference, is one of the typical difference between finite dimensional and infinite dimensional T. I will give a sketch of the proof. The proof is not difficult, but it is needed to consider several a priori estimate. But let me explain the main idea. So the main idea is to consider the penalized equation. This, in fact, is typical to study the Neumann problem. It is well known, the relationship between the normal problem and the penalized equation. Penalized equation means that you add in the stochastic differential equation the extra term Q1 minus alpha beta epsilon x epsilon of t, where epsilon is greater than 0 and beta epsilon is 1 over epsilon, x minus the projection. Pk of x is the projection of k. And for instance, in the case of the ball, pk of x is just ever over x over norm of x. For x and the pk of x is equal to x for x in the ball. So this is the usual penalization problem. It is well known that beta epsilon is Lipschitz, so this problem has a unique solution. This is very easy by a fixed point theorem. And the corresponding Kolmogorov operator is n alpha epsilon equal to the previous one plus this extra term, Q1 minus alpha beta epsilon d phi. Okay. Notice that this operator is of a gradient form, and then it possesses an explicit invariant measure. This is the form of the invariant measure. Ni epsilon is so the invariant measure is absolutely continuous with respect to the Gaussian measure mu, and the factor is just the integral of the potential the potential is e to minus 1 half dk square x. Dk is the distance. Dk of x is the minimum. Z is just a normalization constant. Normalization constant. Just one thing about the previous equation. In fact, this penalization problem is classical when alpha is 1. Because if alpha is less than 1, this operator is not monotone. It's no longer monotone. So the problem is, but concerning existence, there is no problem because it is Lipschitz beta epsilon. Okay, but I will come back on this problem before when I will discuss the relationship with the stochastic variational equation. It is very important to notice that the operator, the nonlinear operator, is monotone only for alpha equal to 1. Otherwise, is not. In any case, for any alpha, it is a gradient system. It is a general definition of gradient system. Is a symmetric, is a reversible, system, and this mi epsilon is the corresponding invariant measure. Now it is natural to introduce an approximating Neumann problem. So given lambda greater than 0 and f in L2 h mi epsilon, we consider the approximating equation. And one can show that this equation has a unique solution and very precise estimate holds. This is not difficult to do, but it requires some computation. For instance, the first estimate is clear. I can write it here. Consider lambda v epsilon minus if you multiply both sides by phi epsilon and integrate and use the inégalité du carré du champ, using the fact that nu epsilon is explicit, you find immediately an estimate for the gradient. And by this estimate, that is, you find an estimate for the square of the function and also an estimate for the gradient. Then there is the problem to find a second order estimate. For this, you take this equation, you take derivative in some direction dh, and you find lambda dh phi epsilon. Use the commutator between derivative and epsilon. This will be minus n epsilon L epsilon, okay, n epsilon dh phi epsilon, plus some extra term which comes from the commutator, and the more important is the derivative of beta epsilon x d phi epsilon. So the idea, as usual, when one wants to find estimate for derivative, take derivatives of the equation and you estimate. Here the problem is that beta epsilon is not differentiable. It's not differentiable. So the computation is more complicated. One has to introduce a further approximation. But then at the end one is able to find also the second estimate. Now, using all these estimates, one can show that the solution, the strong solution, phi epsilon converges to the strong solution, and since all estimates are independent of epsilon, one can show that phi epsilon has the good regularity one wants to have, and also that the Neumann condition is attained, and for this we use the formula for the trace of the normal derivative I indicated before. In order to use everything, what is essential is to have all these estimates. So this will complete the proof of the regularity. Now let me say something which is the relationship between the solution, this abstract semigroup, and the solution of a variational stochastic equation. Formally, this is the variational stochastic equation. There is the equation, the basic equation I showed before, and there is this extra term a alpha minus 1 times nk of x, where nk is the normal cone. The normal cone is the subdifferential of the indicatrix function. And what one expects is to solve this equation and to show that the semigroup which one has constructed before is just the expectation of phi xtx. This would be natural, but in fact we are not able to show this. So let me give what is known. So the best results are in the case when alpha is equal to 1, because in this case a alpha minus 1 is identity, so nk is monotone. In this case, the stochastic variational inequality for monotone operator was studied. There is a theory in infinite dimensional by Sepa, infinite dimensional. In infinite dimensional case, the only case in which when alpha is equal to 1, alpha equal to 1 means that the stochastic term is the white noise. The only result I know in the infinite dimensional case, when one proves directly that the stochastic variation equation has a unique solution, is the result by Noirard-Pardue, I quoted before. And there are general results, in the always in the case alpha equal to 1, which using Lagrangian flow in this paper by Ambrosio, Savare, Zambotti. And they consider a general log concave measure. The case of log concave measure is the case of our measure nu when alpha is equal to 1, and using the theory of Dirichlet form developed by Ma-Rickner, they and the theory of Lagrangian flow, they are able to show that the semigroup is in fact the transition semigroup of an explicit Markov semigroup, which is constructed through the Dirichlet form theory. The situation is much more difficult if alpha is not equal to 1, because the equation is not of monotone type. And in this case, you cannot use the theory of monotone operator, and so for the moment we have a partial result in a particular case when k is the unitary ball B01, alpha this condition trace holds. So this does not hold for alpha equal to 1. In this case, you can construct the process through the usual method by Skorokhod, and the idea is to consider the solution of the stochastic or the approximating stochastic equation, and by using several estimates we are able to this equation to develop the methodology of Skorokhod. That is, you can construct a policy space, a probability space, a sequence of h-valued process, and finally a h-valued stochastic process, which such that the law of x epsilon tilde coincide with the law of x is such that x epsilon converges to x almost surely, and moreover, in this case, the semigroup is just the transition semigroup corresponding to xtx. And moreover, xtx belongs to K. And this is not a very good result. This is just a starting result. We have also to say that we are not able to prove that the xtx is a continuous process, as in the case of Ambrosio, Savarotti, Zambotti, Savaret, but it has only cut-lag trajectories. We hope to be able to improve in the future this result. Now, in the last part of the talk, I will speak about the Dirichlet problem. So, I consider this problem with a Dirichlet condition. L alpha is the Orsten-Uhlenbeck operator I considered before. A first remark, here we have a candidate for the solution, which is given by this deterministic formula. The solution is just the Laplace transform of the stopped semigroup. The stopped semigroup is the expectation of f(x)(tx) multiplied by the indicative function of the time. One requires that the exit time from K is greater or equal to t. This is a well-known probabilistic formula. So, a first remark, one can show very easily that the measure mu is sub-invariant for this stopped semigroup. And so the semigroup can be uniquely extended to a contraction semigroup in L2 K mu. This very simple computation. So why to study this operator in L2 K mu? It will be natural to starting a study of the Dirichlet problem in space of continuous function, Elder continuous function, as in finite dimensional case. But in infinite dimensional case, space of continuous function is very bad because one can show that in infinite dimensional case there are many irregular points. For instance, a ball, which in finite dimensional case is very regular, has infinitely many irregular points. This was shown in a paper in collaboration with Goldis and Zabchik. Also, with Professor Zabchik, we spent at least 4 months trying to show a gradient estimate in the case of continuous function. We are not able. So the problem seems really to be very difficult. For this, I think is a natural idea to try to study the problem in space L2 K mu, since measure mu is sub-invariant. So in this case, the semigroup is known because we have just written the expression. So what we try to do is to show the regularity of this semigroup, the regularity of the solution of the Dirichlet problem. In particular, to show that for any function in L2, the condition that the trace on the boundary is 0 is attained, which is not a priori evident. Let me recall some results in infinite dimension. In infinite dimension, one can prove result of regularity at the interior. This was done in collaboration with Goldis and Zabchik for the first derivative, and Talarczyk was able to extend this result to any derivatives. So she showed that at the interior the solution at T are C infinity. As I said before, it seems to be difficult to study the regularity of the semigroup up the boundary because in general there are infinitely many regular points. For this reason, we should study regularity in L2. In finite dimension, there is a classical theory for regularity in space of C alpha, their continuous function. Also, there is the classical theories by Agmon, Douglas, Nirenberg in W22, and it is also possible, this was done in this paper by Lunardi, Metafune, and Pallara, it is also possible to get maximal regularity results in space L2K mu with respect to the invariant measure. And at the moment, you are only able to get regularity for the first derivative. You are not able to find the regularity for the second derivative, as in the case of Neumann, and you are starting to look for counterexample. At this moment, I think that there should be counterexample to the second derivative. For the moment, we don't know. So this is the main result. This is a gradient estimate, both for the semigroup and for the resolvent, and moreover the fact that both the semigroup and the resolvent vanishes on the boundary of K. This is our main result. And the fact the first estimate are obtained as sketch of the proof. We introduce an approximating semigroup by the Feynman-Katz formula. Then we prove gradient estimate for the Feynman-Katz semigroup. And then we show that the trace of the limit vanishes. So this is the idea. And why we are not able to find estimate for the second derivative? The problem is that this Feynman-Katz semigroup is not very good when you take a derivative with respect to x, because we have obviously one has to take the, you see, g is a function which is 0 to k, is strictly positive outside. So it is easy to show that this converges to the semigroup. But it is difficult to find the second estimate because one should need that G is concave, whereas it is natural that G is convex. This is the reason. Okay. A final remark. In the case of the Dirichlet problem, one can study the problem with lambda equal to 0. For instance, in finite dimension, with k is bounded, it is natural to study the problem with lambda to 0. And in fact, one can show that the operator RT, the semigroup, is compact for all alpha in 0, 1, but with the exception on 0. In the case of alpha equal to 0, is not compact. This relies on embedding theorem of Sobolev embedding theorem, and when alpha is equal to 0, it is well known that the Maillevin W12 space, D12 space, does not embed, is not a compact embedding. But for all other alpha, this is well known. That the embedding of the Sobolev space in L2 is compact. Now, having the compactness of RTK, it is very easy to show a Poincaré inequality. And using Poincaré inequality, we show that this problem is a solution. Just some references I have quoted before. The first paper is the paper with Barbu et Tubaro. Blumenthal-Alligator is another general references on potential theory. HRI is the book I quoted before, together with Dalewski and Fomin. Here there are the paper with Goldis, Zavchik quoted, Talarchik. And the Dinkin is quoted because he studied the finite dimensional case, and in the infinite dimensional case, in order to prove regularity at the interior, we mimic the proof of Dinkin. Gross Hertler is a very important result. In fact, it appeared just on the proceeding of a conference in Oberwolfach at 10 in this lecture note in mathematics. I think it's an important result. I don't know why there are not further signed by Hertler. De Lunardi, Metafume, Pallara is the finite dimensional case studied in L2. Magliavin is the book I quoted before. Noalar, Zambotti. Okay. I think I finish here. Thank you for your attention.
Thank you very much. Are there any questions or comments?
You've looked at the potential theory of an open
Excuse
set.
me, because
Yeah, you have to
he's
speak
too
up.
far. Could you speak?
Could you speak up?
Okay, you looked at the potential theory of an open set inside this Hilbert space. Why an open set? I mean, for the particular norm you started with, I mean, how special were your arguments to the fact that it was an open set?
The open sets.
Yeah, why was it an open set, not a finally open set?
I think
What is essential?
ball, for instance, and then ellipsoid, and these in fact are the regular open set I know. It will be important to try. I think this we will try also to do it. It will be important to extend these results to less general sets, because one has a good integration by part formula when the set is good, but through approximation one can try to generalize this formula in more general situation. This will be important, but it's not easy, because for instance the integration by part formulae proved by Zambotti are very complicated to get in this case. But I have the hope that it will be possible to generalize in some more situations. Up to now is morally ball and sets which are deformable in balls. I think this is.
But in finite dimensions, we were
Yeah, but
with
we
open
dropped the
sets.
openness. We dropped the continuity of solutions. You're only looking at solutions in W12. And then the natural space is the finally open sets.
Can you
If you were doing open sets, you'd look for continuous
Yeah,
solutions. But when you start looking at solutions in W12, then even in finite dimensions, you wouldn't look at open sets.
Can you repeat to me?
Okay, maybe first Martin and then I.
Okay.
Yeah, in the first part of your talks, did you have to assume that the set K was convex?
Excuse me?
Because- Do you have to assume that the set K is convex?
Mm-hmm.
Because otherwise this projection map would not even be continuous.
He assumed that.
Oh, he
That was
assumed
that
that.
was an
Okay.
assumption. Wasn't it?
Sorry.
Any other questions? But then I would like to make a comment directly related to what Terry said. So the point is, of this approach in general is that you look at the Sobolev space of order 1, 2,
Yes.
and then you just restrict it to the set K, whatever your set K is. You can always restrict it. Yeah?
Yes.
And then you can do the following. You can look at all those functions in the Sobolev space that go to 0 at the boundary.
Yes.
So that's the H0 space of K, so going to 0 at the boundary. And you can look at the orthogonal complement of that. The orthogonal complement are exactly the harmonic functions in the weak sense. And they are not continuous in general. That's exactly what Terry was saying.
Yes.
So they're only finely continuous. So the question is whether the topological boundary dk has anything to do with the question. It should be really the Martin boundary, yeah, or the fine boundary. Of course, for nice sets, I mean, for the Laplacian, for instance, we know the ball, even in the Hilbert space, is regular. So all boundary points are regular. But for the Ornstein-Uhlenbeck, this is wrong, as you said. I mean, you proved this in the paper. So therefore, you see that this topological boundary is not the right boundary, because even for the Ornstein-Uhlenbeck, the boundary points are no longer regular. So I think one should rephrase the whole problem, I agree completely with Terry, and replace dk by, for instance, the fine boundary, just as a start.
Yes.
And then do the same thing again. Because also in Lorenzo's case, the set K of positive function L2 has empty interior, so your main assumption is not fulfilled. Also in the Maliavin case, where you have a regular function G less than K, you look at the level set, they typically have empty interior. And this is to do that any Kaplan process on a Polish space is supported by a union of compacts. So it's supported by a set which has empty interior with respect to the normal topology. So that is exactly what Terry was pointing out. I think that the usual topology on the Hilbert space is maybe the wrong topology to study this question. But what you have done is, of course, the first step. I mean, it's the first step, go with the regular topology and see how far you can go, and then you see the deficiencies. So I appreciate very much what you have done, but it's sort of the start.
Yes, yes, yes. This is just a first step.
But even in finite dimensions, you have open sets of the classical Dirichlet problem with many irregular points.
Yes.
Sure.
And okay, I think both questions are meaningful.
That's right.
You don't change topology to have, all points regular.
Right, but if you look at the boundary theory of Silverstein for Dirichlet forms, he always goes to the Martin boundary, because that's the natural boundary for all open sets. And then you can do the entire theorem, because the process gives you the right topology. And I think this is the same here. You should look at the topology that is given to you by the Ornstein-Uhlenbeck process, and it sits on a very thin set, so the regular topology might not be the right one.
Yeah, if I could have one more point, I exactly agree with that point. The process is the more fundamental object. And then you use the process to teach you about the PDE, and not the other way around. And there is a natural boundary, a natural topology that go with the process, and the interesting and hard bit is normally to use that to say something meaningful about the topologies you're interested in. Like, for example, tying the Martin topology with the real topology.
Maybe one last remark, if you allow. The point in finite dimensions is that capacity comes in drastically. But you can look at higher order capacity in finite dimensions, so CRP capacity. So if you blow up the P, you can take R equal to 1, but you blow up the P, at some stage there is no capacity zero set anymore but the zero set. So in finite dimension, it becomes a pointwise theory. And so the fine topology is a natural topology given to you, which you cannot change. It's something natural. This is not true in infinite dimensions. Yeah, so they're the capacities, even if you blow up the R and P, Maliava told us there will never be at the end only the empty set having zero capacity. So I think this theory cannot be done without capacity zero there, without exceptional sets in the sense of Maliava. So there must be some thin sets that you have to exclude, otherwise it's probably not possible. But I mean, to find really the borderline, I think is really a very interesting problem for the future. Okay, maybe if there's no other remarks, we close here and then go for coffee, and thank you very much again.